So, good evening, everyone. Welcome to session 4 of live tutorial on fundamentals of electronic materials and devices. So, these live sessions are brought to you in association with PMRF and NPTEL. So, this is a fourth session, and for the past four sessions, we have been looking at questions that are similar to your assignment questions. And in this week, also, we'll be doing the same. Since no students have joined, this will be a recorded session, and I request so we'll be discussing the questions briefly. So, this session will be rather short. And once you have seen this lecture, please go through these questions by yourself. And in case you face any difficulty, please do contact me or we can discuss in the next class. So speaking of that, for students who has not watched my lectures yet, I am Santhra Krishnan B. I am a research scholar in the Soft Matter and Complex Fluids Lab in the Department of Metallurgical and Materials Engineering at Indian Institute of Technology, Madras. So this is my email ID where you can contact me with your doubts and other queries, santhra.pmrf@gmail.com. So on that note, let us move on to today's questions. So the first question is, which of the following statements is true regarding a metal semiconductor junction? Here, phi refers to the work function. So the first option is the junction is always ohmic when the semiconductor is p-type. The junction is always Schottky when the semiconductor is n-type. The junction is ohmic when phi of the metal is greater than phi of the n-type semiconductor. And the junction is Schottky when phi of the metal is greater than that of an n-type semiconductor. So these questions that we are discussing today will be from week 4. So in this first question, if you see, they're asking which of the following statement is true regarding a metal semiconductor junction. And we know based on the lectures that we saw that it is not possible that when a metal and a semiconductor is in contact, it is not that all the time it will be either ohmic or Schottky. Therefore, the first two options are surely wrong. So the next is the junction is ohmic when phi of the metal is greater than that of the semiconductor, or it is Schottky when it is greater than that of the n-type semiconductor. So if you see, in case of a metal and an n-type semiconductor, when is a Schottky junction formed? A Schottky junction will be formed when phi of the metal is greater than phi of the semiconductor, and an ohmic junction will be formed when phi of the metal is less than phi of the semiconductor. Therefore, here what would be the answer? Phi of the metal is greater than phi of the n-type semiconductor would mean that the junction is Schottky. Therefore, D will be the answer. So just as a note and revision, in case of a junction between a metal and p-type semiconductor, if phi of the metal is less than that of the semiconductor, it will be Schottky, and if phi of the metal is greater than that of the semiconductor, it will be ohmic in nature. So that is the reverse of an n-type semiconductor. So for the first question, the answer will be the junction is Schottky when phi of the metal is greater than the phi of an n-type semiconductor. So I hope this question is clear to all of you. So please go through the sections in your notes and verify. And in case you have any doubt, please do ask. So next is a junction is formed between a metal and an n-type semiconductor. The work function of the metal is given as 5.5 electron volt. The electron affinity and band gap of the semiconductor is 4 electron volt and 1.3 electron volt respectively. What is the Schottky barrier of this junction? Give your answer in volts. So here they have given us a junction that is found between a metal and an n-type semiconductor. The work function of the metal is given, but the work function of the semiconductor, the band gap of the work function of the semiconductor is not given. Instead, they have given us the electron affinity and band gap. So now we have to find out the Schottky barrier. So based on the lectures that we saw, the Schottky barrier 5B is given by phi. What will be the Schottky barrier? Phi b is given by phi m minus psi n. That is the difference between the work function of the metal and the electron affinity of the semiconductor. So basically, when a metal and a semiconductor junction is formed, if you remember from the lecture, this is how the shift of the Fermi level occurs, and there is a band gap, there is an energy level bending in this region, and based on that, the barrier potential EV0 is given by phi m minus phi n, that is the difference between the work function of the metal and semiconductor. And the Schottky barrier phi b is given as phi m minus psi n, and also it is to be noted that phi v is always greater than EV0. So now that you know the equation of phi v, we can solve this question using what is given to us. So here 5m is given as 5.5 and psi n is given as 4. Hence, what would be the answer? 5 would be psi 5m minus psi n given by 5.5 minus 4, that is 1.5 electron volt. So that is the answer to this question. So I hope this is clear to all of you. So in that case, let us move on to the third question. So in a PN junction, what is the relation between built-in potential and Fermi levels in the P and N sites before the junction is formed? Take the reference for the Fermi level to be the top of the vacuum level for both P and N sites. So first option is built-in potential is the sum of Fermi levels on the P and N site. Built-in potential is the average of Fermi levels on the P and N site. Built-in potential is the difference of Fermi levels on P and N site, and the final option is the two quantities are not related. So if you remember how a PN junction is found, we have a p-type semiconductor and we have an n-type semiconductor, and we know that there will be an electron flow from the p-type to p side to the n side, and at equilibrium the Fermi levels will line up, and the built-in potential in that case hence would be given by EV0 is equal to 5p minus 5n, and hence when the equilibrium PN junction is formed, this would be the diagram, and EV0 is given by 5p minus 5n. Here we can see that work function of p-type will always be greater than work function of n-type, and hence bending would be in this direction, and hence EV0 will be given by 5p minus 5n. So hence the answer to this question will be the built-in potential is the difference of Fermi levels in the P and N side. So these are actually revision kind of questions, that is that's purely direct based on the videos that you have seen. I hope that all of you have gone through week 4 lectures. So in week 4 lectures, we have similar topics that are discussed: how a metal semiconductor junction is formed, what is the difference between Schottky and ohmic junctions, how a PN junction is formed, and in the next lectures you will be seeing what would occur when we are applying bias to such junctions. So on that note, let us move on to the fourth question. A junction is formed between a metal and an N-type semiconductor. The work function of the metal is 6.1 electron volt. Electron affinity and band gap is given as 3.6 electron volt and 1.3 electron volt respectively. What is the Schottky barrier of this junction? So give your answer in volt. This is very similar to the question number 2, I think, that we have just solved. So this is actually a practice question for you. Here also a junction is formed between a metal and an N-type semiconductor. Work function of the metal is directly given to you, and for the semiconductor the band gap and electron affinity is given to you as 3.6 and 1.3 respectively. So we have already said that Schottky barrier of a junction is given by the difference between work function of the metal and psi of the semiconductor, that is 6.1 and 3.6. So in that case, when you subtract 6.1 and 3.6, you will be getting the answer as 2.5 volt. And for those people who want clarification regarding how we calculate the Schottky barrier is given as the difference between phi m minus phi n, that is the work function difference of the metal and semiconductor, plus EC minus EFN. EC is the conduction bar and energy level, and EFN is the Fermi energy level. So when you are consolidating this equation, finally we will get phi m minus psi n. So here it's clearly mentioned that phi m is the work function of metal and psi n is the electron affinity of the n-type semiconductor. So basically usually it will be such that all this data, like whatever is required for calculation, will be given to you. In our case, phi m and psi n is directly given, hence we get to calculate 6.1 minus 3.6 is equal to 2.5 electron volts. Sorry, not electron volt, volts. So that is the case. So the fifth question is, consider an n-type sample with 10 power 17 donors per centimeter cube. The electron affinity of silicon is 4.01 electron volt, and the work function of 4 potential metal For contacts are as follows. For cesium, it's 1.8, lithium 2.5, aluminum 4.25, and AU 5 electron volt. For silicon, EG value is given as 1.10 electron volt. Ni, that is the intrinsic carrier concentration, is 10 power 10 centimeter per centimeter cube, and EFI is 0.55 electron volt. Now we have to find or the correct statement regarding the work function of the n-types and the type of contact with the metals at a temperature of 300 Kelvin. So here an n-type sample, that is the semiconductor, is given to us, and to give a contact for this semiconductor there are a choice of four metals, but when these metals are joined based on the what work function of silicon and the work function of these metals, they will be forming either Schottky or ohmic junction. So first, in order to know that, we need to find out. So in our case, the work function of the four metal contacts are given, but we need to find out the work function of the silicon sample. And for the silicon sample, we have the electron affinity, and we have the n values and intrinsic carrier concentration, and EFI is also given. So based on that, first we have to find out the phi value for silicon, and then compare the phi value of silicon with the phi value of the metals that are given. So once you know that, you can identify the work function of silicon out of these four values, what is the answer, and which of the metals form Schottky junction and which of the metals form an ohmic junction. So first let us start by finding out the work function of silicon. So the Fermi level position of an n-type semiconductor, intrinsic semiconductor, is given by EFN minus EFI is equal to KB ln T n by Ni. Here what all are given to us, EFN is the one that we have to find out. 0.55 EFI is given to us. KB and T are constants. So in case you are substituting all your values in electron volt, please do substitute KB also in electron volt. T is in Kelvin, that is at 300 Kelvin we have to find out, and here both N and Ni, that is the n-type carrier concentration 10 power 17 is given to us, that is the Nd value, and an intrinsic carrier concentration is also given to us. Upon substituting Kb and T in this particular equation, we will get the EFN value as 0.967. We also know that the electron affinity is given to us, right? So the work function of the n-type semiconductor can be calculated using the following equations. And that is the work function of the n-type semiconductor is equal to Eg minus EFN plus psi n. And here we know that both Eg and psi n are given, and EFN we have just calculated. Therefore psi n is equal to 4.01 and Eg is equal to 1.1. Along with substituting with 0.967 in this equation, we get phi n as 4.14 electron volt. So out of the four options, we can select the one with 4.14 electron volt. But in case there are multiple 4.1 for electron volt, then we have to compare. So since phi n is 4.14, for cesium and lithium, this will be greater. Hence, an ohmic junction will be formed. And in case of aluminum and Au, 4.14 will be less than their work functions. Hence, Schottky junctions will be formed. So if you see here 4.14, there were two options, and out of these two options, C will be the answer. Aluminum and Au form Schottky junctions, while cesium and lithium form ohmic junction with the semiconductor. So as a recap, I would say first here N value is given, electron affinity is given, and work function for four other metals are given. So basically we have an N-type silicon sample and four metal contacts, and we have to find out whether these are Schottky or ohmic junction. So how do we do that? We have to compare the phi value of these metals with the phi value of the n-type silicon sample. To find out the n-type phi value, we have to use the n value, the Ni value, and use the equation EFN is a EFN minus EFI is equal to KB ln T n by Ni. So that equation we have to use, and we have to find out the work function of the silicon sample. And then upon comparing these two values, we will be able to see which of the metals will give us Schottky junctions and which of the metals will give us ohmic junctions. So I hope this question is clear. So now we can move on to the sixth question. A silicon PN junction is formed with donor and acceptor concentrations of 10 power 6 per centimeter cube. If intrinsic carrier concentration at 300 Kelvin is 10 power 10 per centimeter cube, what is the built-in potential? And we have to find the answer in volts. So basically, ND is given to you, NA is given to you, NI is given to you, and temperature is also given to us. So V0 is equal to KT by E, ln Na ND by Ni square. So upon substituting K value, that is 300 K 1.38 into 10 power minus 23, temperature is 300 Kelvin, E that is the value of an electron, that is 1.6 into 10 power minus 19 ln 10 power 16. So this is actually 10 power 16. Okay, that's a mistake. And 10 power 20, that is Ni. 10 power 10 was the intrinsic area concentration. Since it is square, it is 10 power 20. This is actually not 1016, it is 10 power 16. Okay, so when you substitute all these values, we will get V0 as 0.71 electron volt. So B will be the answer. This is a rather direct question. Basically, you have to just remember this equation. V0 is equal to KT by E ln NA ND by Ni square. And please do remember that whenever we are substituting K value in electron volt, the corresponding values will also be obtained in electron volts. Otherwise, we have to substitute both of them in joules wherever energy values are involved. So I hope this sixth question is also clear to you. So next is, consider a short Key Junction diode between AU and N silicon with 10 power 16 donors. The electron affinity of silicon is given and work function is given. Ni is given as 10 power 10 per centimeter cube. The band gap of silicon is 1.1 electron volt, and assume that Nc is equal to Nv for this question. What is the built-in potential? Give your answer in B. So again, a short Key junction is formed. Electron affinity of silicon is given. Work function of AU is given. Ni is given to us for silicon. The band gap of silicon is given. And it is told that we have to assume that Nc is equal to Nv for this particular question. So intrinsic carrier concentration Ni is given by root of Nc e power minus Eg by 2 times Kb into T. Nc and Nv are effective density of states, and Eg is the band gap of the semiconductor. So it's also given to us Nc is equal to Nv. So basically, in this equation, we have Ni. We don't have Nc and Nv, but we know that Nc is equal to Nv. Therefore, basically, it becomes Nc, and therefore root of Nc square, and hence it becomes Nc alone. E raised to minus Eg by 2 times Kb into T. 2 times Kb into T is a constant when it's given that if the temperature is 300 Kelvin, and Eg is given to us as, what is the band gap? 1.1 electron volt, and hence we will get the value of Nc as 1.738 into 10 power 19 per centimeter cube. Now we have to find out the built-in potential. So built-in potential, we know that using the equation, and also in an n-type semiconductor, the relation between electron concentration and Fermi level is given by n is equal to root of Nc Nv only here also, but since Nc is equal to Nv, again it becomes root of Nc square, and hence Nc alone. And hence the equation becomes n is equal to Nc e power minus Ec minus Efn by 2 times Kb, and by Kb into T. And substituting the value of Nc, we will get Ec minus Efn as 0.19286 electron volt. And finally, built-in potential in the short Key junction will be given by phi m minus phi semiconductor, or phi m minus psi, that is the electron affinity of semiconductor, plus Ec minus Efn. This Ec minus Efn we have already calculated from this part. The phi m is given to us, psi semiconductor is also given to us. So this is the important part. Once we find out Nc using the intrinsic carrier concentration equation, it has to be substituted such that we need to find out Ec minus Efn. So usually we know EV0 is equal to phi m minus phi semiconductor, but on expanding phi semiconductor, how it will be? Psi semiconductor plus Ec minus Efn. So in order to find this Ec minus Efn, we need to go to this equation, and here Nc was unknown, and to find the Nc we had to use the equation for intrinsic carrier concentration. Now that we have all the values, Ec minus Efn is given, Ec xi semi is given, phi m is given, we can get V0 as 0.797 volts. So I hope it's clear to you. So once again, I'll just briefly go through. Basically thing is that we have to find out the built-in short key junction potential EV0. For that EV0 we need EC minus EFN. To find EC minus EFN we have to use the equation N is equal to root of NC NV e power minus EC minus EFN by KB into T. But here NC was unknown. Hence we can use the intrinsic carrier concentration root of NC NV e raised to minus EG by 2 times KB into T. There NC is equal to NV was given, hence we got the value of NC. And upon substituting here we got EC minus EFN. And once EC minus EFN is known, rest all are given to us and we can find EV0 as 0.797 volts. So I hope this question is clear to all of you. And now we'll move on to the eighth question. Calculate the width of the depletion region in a germanium PN junction where the acceptor concentration and the donor concentration are 10 power 16 per centimeter cube and 10 power 18 per centimeter cube respectively, and intrinsic carrier concentration is 2.4 into 10 power 13 per centimeter cube. Take the temperature to be 300 Kelvin and the relative permittivity of germanium to be 16. Give your answer in mu m and choose the nearest value. So basically ND is given to us, NA is given to us, and Ni is also given to us. Temperature is 300 Kelvin and here the relative permittivity epsilon R is 16. We know that V0 is equal to KT by E ln Na and D by Ni square. Basically all of those values are given to us. We have to substitute 1.38 into 10 power minus 23 for K, 300 for T. Charge of an electron is 1.6 into 10 power minus 19 coulombs, and ln of 10 power 24 into 10 power 22 by 2.4 into 10 power 19. Here please note that everything is being converted into meters so that we get the answer in volts basically, but inside the ln even if you convert or not, basically since it is a like division, it will be cancelled out, hence it is not necessary, but if you want you can convert all the units to SI. So V0 will be 0.43. So once you have got the value of V0, we can calculate the width of the depletion region as 2 times epsilon Na plus Nd V0 by E Na Nd. So 2 times of epsilon is given. So 10 power 12 into 16 plus 2 10 power 24 plus 10 power 22 into 0.43. All these values are given to us. Hence, we get the value of W0 as 0.28 micrometers. So it's rather direct once you get the value V0. Like equations are known to us. First equation that is required is V0 is equal to KT by E ln Na Nd by Ni square. And then we have once V0 is known using this particular equation 2 times epsilon and A and E V0 by E Na Nd the whole root we can find W0 as 0.28 micrometers. So next is question number 9. In the silicon PN junction, if doping concentration in the N region is much higher than the doping concentration in the P region, the depletion region dash lies mostly in the P side, lies most entirely in the N side, is equally distributed on either side of the junction, do not exist on either side. So this can be found out from a relation that connects the carrier concentration along with the depletion width. So this is the equation Wn by Wp is equal to Na by Nd. Basically, it's oppositely matched, right? With an n side in the numerator and the whole concentration in the numerator. Therefore, Wn by Wp and Na by Nd. Here it is given that if the doping concentration in the N region, which means that Nd is much greater than Na, which means that Wp would be much greater than Wn. That is, width of the P region would be much greater than width of the N region, which means that the depletion region will most entirely be in the P side itself. Therefore, this particular question, the answer would be lies almost entirely in the P side. So next question is, which of the following is the correct order of increasing built-in potential for a PN homo junction using the following materials? Assume dopant concentrations are same and all the junctions are at room temperature. Since it is mentioned that dopant concentrations are same, one thing that could be influencing would be the intrinsic carrier concentration. So how would that be? We know that the built-in potential or the contact potential is given by V0 kBt by E ln Na Nd by Ni square. But here they have mentioned the dopant concentrations are same in all cases. Therefore, V0 will be proportional to ln 1 by n square. Since the dopant concentrations are same and all the junctions are at room temperature, V0 is proportional to ln 1 by Ni square. Hence, based on whether Ni square increases, then V0 will decrease. Now, intrinsic carrier concentration of these materials, if you see for silicon, it is 10 power 10, it is 2.0 into 10 power 13 and 2.4 into 10 power 6. And we got from the equation that Ni is inversely proportional to the V0. And hence, clearly, if you see here, V0 of germanium less than V0 of silicon less than V0 of gallium arsenide. Why? Because germanium has the maximum number of intrinsic carriers, hence it would have the least amount of built-in potential. Silicon would be the second with 10 power 10 and 2.4 into 10 power 6 is the least of intrinsic carrier concentration, and hence it has the maximum V0. Basically greater the Ni, lesser the V0, and that was found out using the equation kBt by E ln Na by Ni square. Hence, here since kBt, E, everything is constant, only thing that is left to us is V0 is proportional to ln 1 by Ni square. So that is how we came at this. So I hope the question was clear. Whatever we discussed until now is clear to you. We'll move on to the 11th question. Suppose a junction is formed between lithium and Au. The work functions are 2.5 electron volt and 5 electron volt respectively. Choose the correct statements. Please note that more than one answer might be correct. This is a rather direct question. So basically, a metal junction is formed between lithium and Au, and work functions are given as 2.5 and 5 electron volt. So what happens? We all know that when something, for in our case at least, lithium has 2.5 electron volt and Au has 5 electron volts, right? The work function of lithium will be less and the work function of Au will be more, and hence what will happen? A net positive charge develops on lithium and a net negative charge on Au at equilibrium. This is because this is true. This is because we know that for a material which has the lower work function, there will be a net electron flow from lithium to Au. Right, electrons will move from lithium to Au, and as a result, a net positive charge develops on lithium and a net negative charge on Au. Hence, A and B will be correct. The contact potential at the junction is 2 electron volt. That won't be the case, right? Even if that it were the case, it should be 2.5 electron volt. That is because the contact potential would be the difference between the two. Hence, 2 electron volt is not correct. C is not the correct option. The contact potential at the junction opposes further movement of electrons once equilibrium is reached. That is a known fact when such junctions are formed. Hence, from this question, we can clearly see that options A, B, and D are correct. Option C is wrong. Hence, for these questions, a positive charge develops on Li and a negative charge on Au. Electrons move from Li to Au, and the contact potential at the junction opposes further movement of electrons once equilibrium is reached. All these three options are correct. So next question is, the total depletion width of germanium PN junction is 1.5 μm. The donor concentration is 2.10 power 15 per centimeter cube and acceptor concentration is 5 into 10 power 14 per centimeter cube. What is the depletion width on P side of the junction? Basically, what we have to find out, total depletion width is given to us. That is, we don't know separately Wn and Wp, but total depletion width we know. And the donor and acceptor concentrations are also given to us. So how do we find out from this particular case? So basically what you can simply do is add 1 on both sides, and then what will happen? Wn plus Wp, but basically we are adding 1 over here so that in the numerator we have Wn plus Wp, and that is basically the whole W value, and rest all values are known to us and we can find out Wp. Suppose you wanted to find a Wn, what would you do? You would simply flip over these two, that is Wp by Wn is equal to Nd by Na, and again you can add 1 on both sides. We are adding 1 on both sides because here the total depletion width is given. They have not given us separately Wp and Wn, and in order to get the total depletion width on the numerator, we are adding 1. So that became Wn plus Wp, and then we can directly substitute Wp by W0 is equal to Nd by Na plus Nd. And upon substituting, we get Wp as 1.2 mu m. So in these questions, now I am discussing the steps alone since no students discussions are going on. So in your free time, please do solve these questions by yourself, and wherever you feel that you're losing some connection or you have some doubt, please do solve these questions and get back to me. So since this is a recorded sessions, I'm not showing any of the lengthy steps or the calculations that are involved. I'm discussing only the conceptual part. So please do solve these questions by yourself and ask me in case you have any doubts. So next is consider silicon based PN junction. Na is given as 10 power 15 per centimeter cube and Nd is given as 5 into 10 power 16 per centimeter cube. Take intrinsic area concentration of silicon at room temperature as 10 power 10 per centimeter cube. What is the built-in potential of this junction? So this kind of a question we have already discussed. V0 is equal to Kt by E ln Na Nd by Ni square. So that was the equation. So in that case also, Kb is a constant, T is known as 300 Kelvin. In case T is not mentioned in your question, please do take it as 300 Kelvin, and E is the charge of an electron, that is also a known constant. Na and Nd and given to you, and Ni square is the intrinsic area concentration. Therefore, upon substituting, we will get the value as V0. This is exactly similar lines as ones we have solved earlier. So please do try this question as well. So as a continuation to this question, for the silicon based junction, so the junction spelling is wrong in the previous question, what is the total depletion width at equilibrium? So epsilon 0 and epsilon r are given to us. So basically what is epsilon is equal to epsilon, sorry, so here epsilon r is given to us and epsilon 0 is given to us, and once you have epsilon r and epsilon 0, you can find the value of epsilon. That is, this is a relative permittivity and this is the permittivity of free space, right? So basically using the equation, depletion width can be written in terms of V0 as 2 times epsilon 0 epsilon r V0 Na plus Nd by E into Na Nd the whole root. So basically epsilon 0 epsilon r will give us epsilon, that is epsilon is equal to permittivity of free space into relative permittivity. So epsilon r, what is basically epsilon r? Epsilon r is basically permittivity of medium to permittivity of free space, right? So from that we can find out epsilon. So in the previous question it was directly given as epsilon and the value of epsilon 0 was not given. So that could be the case in your examination. So it's better. Usually constants will be given, just in case it's not given, it is a known constant as 8.854 into 10 power minus 4e. So once V0 is known to us, V0 we have already calculated in the previous question as 0.70, and the V0 that you have obtained, you have to substitute over here. Rest all is given in the question itself, and using that you can find the value of the depletion width. So these are the questions for today, and the answer would be 0.97 micrometer. So these are the questions for today. So in your free time, please do try to go through the session so that when you attend the live session in week 5, you'll get some kind of a continuity and solve these questions by yourself. And whenever you're facing difficulty, please do post your queries in the discussion forum, or you can mail me at santra.pmarik@gmail.com. So thank you very much for your time. Hoping to see you next week on Tuesday from 6 p.m. to 8 p.m. Thank you so much.